Good.
Okay, so hello everyone. Welcome to this webinar. This is Climate Change Estimates for the Coming Months, Practical Pilot Services, Part B. And it's nice to see that there's at least some participants already, and I think joining us some more after some minutes. But yeah, my name is Katrina Veijola, and I'm from the Finnish Meteorological Institute. And this is the 7th webinar of the eShape project's webinar series that is presenting pilots from different showcases in the project. And the webinar today is presenting showcases from climate pilots from Climate Showcase, and the Climate Showcase leader Mikko Stralendorf will be joining us a little bit later today, and he will be keeping the closing of the webinar. And this is the part B of the webinar, and the part A of the webinar was in April, and it was more dedicated on forests. And if you missed it, the recording is available in eShape's YouTube channel, and you can watch it there. And in today's webinar there will be, for example, a presentation about hydropower. And if you don't know about the project, eShape is a European project that ensures to maximize Earth observation-based benefits, and it delivers services that use Earth observation for different stakeholders, such as decision makers, citizens, researchers, and industry. And the webinar today will give you information, for example, about climate change estimates in hydropower and global carbon and greenhouse gas emissions. And the main purpose of this webinar is to make people aware of these pilots and to these pilots that give climate change estimates that can predict the situation for the coming months. For example, to be able to prepare and plan hydrology related issues such as hydropower management, as well as to estimate and find improved information about global carbon and greenhouse gas emissions. And I can share the agenda. If you can see it.
Yeah.
So there's a slight change in the agenda. So Tarek Habib is giving the first presentation, and then the others are giving the presentations a little bit later. And so after this introduction, there will be 5 amazing presentations about pilots, about hydropower from snow. I mean, first is the rapid air quality service, and then hydropower from snow, and then global carbon and greenhouse gas emissions. And after that, weather and climate service for UNESCO cultural heritage monuments, and then future climate projection of heat indices for Austrian major cities. Yeah, so I'll just try to stop sharing there. So For those who have joined now, later, for your information, this will be recorded. And then I think we can start with the first presentation.
Great, yeah.
But a little bit yet that you can send questions in the chat, and we will try to answer them after the presentation or then in the dedicated questions and answers session later in the webinar. So the first presentation topic of the first presentation is Rapid Air Quality Service, and it's presented by Tarek Habib from Murmuration. And well, you can start sharing your presentation, Tarek.
Sure. To do this presentation mode, does this work? Seems so. Can you see my screen? The presentation screen? Yeah, all good. Great. So thanks a lot for this presentation slot and for accommodating the agenda. Really appreciate it. So I'm going to go through the service that we are providing, that is Rapid Air Monitoring Service. The presentation is split in several parts, so I'll start by presenting Murmuration, just a couple of slides, just to remind you what we do. Then I'll move with our super resolution model for NO2, based on the Copernicus Atmosphere Monitoring Service data, and then to the CO, so estimation and what we are foreseeing or what we already did for the CO part, and how to take this further in the next couple of months. And finally, conclusion. So let's jump into it. So first, Murmuration. So what we do is really what we call environmental quantification. So basically, we split the environment into 5 domains, the ones that you can see here: water, air, biodiversity, infrastructures, and finally tourism statistics. Why tourism? Because this is a domain where it's more practical to be able to extract or isolate a human contribution or impact on the environment. So that's our approach. For each one of these domains, we derive indicators to quantify the state of the environment related to each one of these domains. When it comes to air quality, we provide our users, this, for example, is work that we did for Malta. It's for the Malta government, air quality service, to show them what are the drivers of air quality in their area and how they compare to other regions around the Mediterranean. So this is the type of final products that we deliver. So what I'm going to present here, so when NO2, CO, etc., the objective is at the end is to integrate it to this type of visualization dashboards. Problem statement. So when it comes to air quality, we have 2 major sources of observations. So that's the satellite data and in situ sensors. I'm not talking about modeling yet, but it's so the sources of observations are really these 2, with the trade-off. One is providing better coverage with the less resolution, and the other is the inverse. So this is a situation just to show this type of trade-off. So on the left side, we have the data coming from CAMS, for example. This is over Paris, test that we've done over Paris. This is the information that is provided by the satellite. While for the in-situ data, we can see that there are areas where we have peaks of NO2 that are not detected by the satellite. So what we're trying to find is really a compromise between the 2. There's no replacement of technology. It's really just to have a model that sits in between and that provides high coverage data with reasonable local resolution and precision. And obviously, this kind of feeds in the modeling process and can provide better modeling. Data and processing. So for the NO2 part, this is what I'm getting into now. We are using CAMS data. We are using the ERA 5 data from ECMWF, so modeling of meteorological variables, so precipitation, temperature, wind, and so on. Copernicus land for topography, population density. This is data set coming from Facebook that is actually quite useful. TomTom statistics that about traffic flows, because NO2 emissions are mainly related to the transport sector. And finally, for the validation of the model, we are using the network that is called in Paris, that is called Air Tarif. There are similar, we have validated on other areas, but what I'm presenting here is really the validation that we did with the Air Tarif data. So that's an in situ network of about 42 sensors, if I remember correctly, across Paris, providing NO2 data. The data processing, this is how it looks like. So it's basically you have geolocalized data or geodata that is we are familiar with, raster images, for example, for land, atmosphere, climate change service. All of this comes in raster. The human density is point data, providing the human density across Paris. TomTom data is also vector format. And finally, Air Tarif is really point data across Paris. So we create a data cube with the data that is required for the model. That's the top 5 data sets. And then for the Air Tarif, we project it on the same grid just for validation. So it's not an input for the model. Simple process is that we homogenize the data, we put it on the same grid. And then we put it in the regressor that is called XGBoost. So it's quite it has good performances. And then we have the NO2 predictions at the end. This is how the results look like, just from a visual aspect. I'll put some quantified measured later, but just to show you on the left side, these are the measurements that we have from the observation, that comes from the CAMS models. So these are cells of 10 kilometer per 10 kilometer, and on the right side we have the data that is the output of our model. So it's a 1 kilometer grid. So we go from 10 kilometer to 1 kilometer using the data sets that I mentioned earlier. To get back to the slide that I've shown in the beginning, so here at the middle we put the model prediction, and we can see that the model is kind of better mimics the in situ data, or gets closer to the in situ data. So again, this is visual results. Now getting more into the actual validation activities, the lines that you can see in red, this is the CAMS NO2. In blue, this is the validation in situ data, and I think it's gray, but I'm colorblind. But the team usually always does this. But it's so I think it's gray, and it's you can see the advances or the fit that the model brings. We have an R2 score of 90%, more than 90%. So that's quite a progress with respect to what is provided directly from the CAMS data. And then we applied as well explainability because this is basically for our model, just to understand what are the drivers of the model and what are the major impacts. So this study again, we'll be happy to share, but just to show that basically all the parameters are relevant, with the exception probably for the date or weekday, that doesn't really play a role. But when it comes to meteorology, for example, variables to the topographic, population density, road traffic, all of these are strong drivers for the model. So that puts what are the major sources of data that we are using and how important they are at the output. Now, how about the application for CO estimations? What we want to do, and this is something we didn't implement yet, is to basically the processing chain that you've seen earlier, to keep it, and instead of using the traffic information and the road network is actually to use the land cover, because the CO emission mainly comes from, for example, isolation from buildings, from problems with isolation, or related to heating, for example, stuff like that. So this is why our idea is to implement this for CO emissions, keeping the same processing chain, the same process, but removing the data coming from traffic and replacing it with land cover, focusing mainly on residential area and industrial area. And this would be the input for the model. The first step that we did, though, is that we deployed processing chain on the environment provided by ICOS, just to compare CO data coming from satellite observations and the ICOS stations data. So that would be our source of validation. Remember, we used air Paris for NO2. Our idea is for validation for CO is to use the ICOS data. So here we did this. The first step is actually to deploy on the ICOS environment. So this is what we did, and to start to compare data coming from satellite data and the ICOS stations, just to map them one-to-one, to see what is the current correlation between the daily observations and the monthly observations. We already see that with taking large time windows, this is something that is already has a good match, has good correlation between the two. So we are in this process now, and the objective, as I mentioned, is to integrate the land cover, to train the same AI model to see how it adapts to these data sets, and to get estimates for the CO emissions in an urban setup. With the objective is to give decision makers with the type of interfaces that we've seen at the beginning, a tool to visualize what are the sources of CO in their area of interest. So that's basically a recap of what I just mentioned. That's it for me. So I'm happy to take questions if you have any questions. Otherwise, do not hesitate to contact me asynchronously after this presentation by email or on social media.
Thank you, Tarek. So at least there's no questions in the chat, but it was very interesting presentation, and it was nice to hear about the air quality monitoring service and combining the in-situ data and satellite data. So
thank you.
Does anybody of you have any questions? So maybe we can then go to the next presentation. So the next presentation the topic is the hydropower from snow, and it's presented by Jaakko Ikonen from the Finnish Meteorological Institute.
Okay, yes, I'm not share my screen. Let's see if this works. All right, can you guys see my screen?
We can see it, but it's it's not the full screen. You know, it's we can see if you have notes, for example, we can see it. Yeah.
Okay, how do I see it?
It's a question of display. Probably you have two monitors.
Yeah, I do.
Yeah, so it's I think.
Do I need to? Oh man, that's gonna be a problem. Actually, let me let's do this. I'm going to close my notebook. Maybe that'll help. Let's see.
Oh.
How about now?
We cannot hear you that well, but it's yeah, but it's in the presentation mode.
You guys hear me now?
Yeah.
Okay. Well, I'm just gonna dive right into the topic. So in the north, or northern latitudes, as in what I would presume in mountainous areas, in more southern latitudes, snow is particularly important for hydropower production, obviously. And well, this is mainly because, for example, here in in northern Finland, spring snowmelt during inflows to hydropower reservoirs accounts for about 55 to 70% of total annual inflows. So, which means a large part of the energy that can be produced is or it's coming in a very short amount of time in the spring when the snow melts. So basically, for this, information on snow reservoir energy potential is critical. So what we need to know in advance, preferably, is snowpack area volume and then the melt rate and timing of that pack. So it's very important for hydropower companies. They also have, well, these hydropower companies, for example, here in Kemijoki Basin, northern Finland, they have like a dual purpose. So they have to also they have to produce energy and optimize that, as well as provide flood protection. So it's kind of a dual thing. So and they need to try to store as much water in the reservoirs for periods where there's higher demand, because during the springtime typically there's lower demand for energy, so the energy price, of course, is lower. So for this, the hydropower company Kemijoki Oy would of course like to know in advance what's going to happen. So to that end, we've been working on a hydrological forecasting system for them. So basically, this is a web service at the moment that's running on FMI internal servers. So what we're providing is a 10-day deterministic hydrological forecast, and then a once a month driven 90-day seasonal forecast with 51 ensemble members. The service comprises basically of three primary components. So there's a land surface parameter modeling component. So this is a in-house developed hydrological model called HOPS. It's a gridded, spatially distributed 5 by 5 kilometer conceptual model, and it has parameters that have been assessed through a priori parameterization with GIS data. So there's very little calibration involved. So typically, models like this require a lot of calibration, but ours, we've been trying to just rely on available GIS data sources. The second component, or primary component, is a Streamflow routing model. So what this does is it connects these HOPS grid cells to each other, and then allows water to flow downstream through a river network. The third primary component is consists of like external data. So for data simulation, for example, we use Earth observation, snow water equivalent data, and then we have in situ observations for validation and calibration for the snowpack model. I'll get to that in a bit later. And there's a new component, or relatively new. It's still less than a year, but we've added a machine learning based Streamflow forecast to the system as well. So yes, the first component is pretty much it's in-house developed land surface model, pretty standard, nothing in particular. Takes precipitation and snow melt, potential evapotranspiration, and 2-meter air temperature as input. So, and it provides basically as output soil moisture fluxes, and then soil temperatures in 4 layers, and also handles surface and subsurface flows. So on the web service, the output of this component looks sort of like this. So what we provide is or maps of 20-day hindcasts and then 10-day deterministic forecast. So this 2D maps, and it can be clicked anywhere, and then you can get plots or time series plots from anywhere in the basin. And we also have included these sort of fixed points, which show the trend in the data. So, for example, if we have do we have a soil moisture upwards trend or a lowering trend, and so forth. So then the second component is the Streamflow routing model. As I said, it provides like a conceptual cell-to-cell link. So it links these hops land surface cells to each other. And also, it also handles flow regulation, such as dams. But in order to do that, we need the dam operation rules, or historical sort of time series for reservoir discharge. That's quite difficult, and of course it's difficult to forecast what a human operator will do. So therefore we only provide inflows to those reservoirs where we can to Kemijoki.
Sorry, Jaakko.
Yes.
I don't see the whole slide. Do you others see that? I mean, there's something I'm missing on the right side, so it's not showing the whole slide.
Yeah, it's in a way too big. Doesn't fit to the screen.
I don't know. How can I fix this? Should I go back and try to fix it, or what should we do? Do you have any suggestions?
Well, maybe it's then visible if you add the slide set to the Confluence.
Yeah, let's do that. Yeah, that's kind of a shame. I wanted to show some things, but okay. Well, let's just move forward then. I'm sorry about that. Should have maybe tested this in advance. Anyway, so yes, so the Streamflow component. This is what it looks like. I'm not sure if you guys can now see it on the web service. So it's just another dialog. Basically, it has the 2D maps from the land surface model, and then superimposed river network on top, and then fixed points for where we're doing Streamflow forecasts. And then you can click on any point, any Streamflow forecast point, and it provides a short-term 30-day and 90-day sort of window with a 10-day forecast. Then there's a long-term hindcast that spans several years, so you can see how the model has been doing in the past. And then also a seasonal outlook dialog on the right-hand side. So as part of the third primary component, so we've implemented a machine learning-based Streamflow forecast algorithm. So this model takes 3 different types of predictors. So atmospheric predictors, such as precipitation, minimum and maximum temperatures for each single day. And those are lagged in time, sort of, but it's tested that what kind of lag is suitable. So it's automatically testing that. And there's autopressive predictors, which are the Streamflow measurements themselves. So it's trying to find a good fit for them. And then there's temporal cycle predictors, which basically mean we're taking into account which season it is. So different seasons have sort of slightly different parameters. So all these predictors are combined and then fitted also into an XGBoost model, as with the previous presentation. And then as a post-processing process, what we're doing is, so we have a raw forecast, and then we adjust that forecast for the first 3 days to try to fit to observations as much as possible. And then sort of there's different weights that are provided into the future to produce a optimal forecast for Streamflow. One of the problems here, of course, is that we can only produce these forecasts for points that actually have observations. So there are a few points within the basin where there are no observations, so we just have to rely on the HOPS model only. Then we also, as part of the third primary component, so we're also assimilating snow remote sensing data. in various ways, basically. Well, direct assimilation, we're using Global CO₂ snow water equivalent data. So we're feeding that, or sort of assimilating that to the HOPS model to correct the snowpack information or state. We're also using optical fractional snow cover products, but this is mainly used for sort of qualitative and visual verification tasks. And this is actually done by the hydropower company, so they just want to confirm sort of what they see on the ground. And it's very difficult to use this in an operational setting for the model or for the service. And also, what Kemijoki, the hydropower company, what they do is they conduct aerial snow coverage reconnaissance flights. So they have sort of predefined path with it, what they always fly every year, so visually inspect and see what the situation on ground is. As part of the assimilation of Global CO₂ data, so what we do is we take the Global CO₂ field information and then also precipitation information, and we adjust the precipitation input to the model based on what the snowpack ground truth according to Global CO₂ is. It doesn't we're not directly ingesting it, we're sort of just nudging the model. So if you can see these, unfortunately, again, I'm not sure if you guys can see, but there's an animation here showing the effect of this assimilation on the model output. So it doesn't exactly mimic the satellite data, but it sort of nudges it. And in particular, during the snow melt season, that's when the satellite data is least reliable. So it doesn't sort of take that data into account. And here's just a quick 2 examples from 2 points in the basin from last year. So what was the effect of simulating the Earth observation SWE data? So on the west-hand side, there's Maraskoski. We can see that it had pretty much very little effect. So that means that that the model and the satellite data sort of agree. So the result is more or less the same. However, in the sort of eastern part of the basin, there was a very significant improvement in the forecast when we used satellite data. You can see it on the graphs below if you can see them. So anyway, so there's a few more slides on the spring forecast for this spring. So this is what we're looking at here. Again, if you can see, is sort of the outcome of the 10-day deterministic forecast. And it's quite interesting that unfortunately this spring on the western side of the basin in Maraskoski, the HOPS model got things quite wrong, meaning that we still need to work on the snow melt model. So what we were predicting snow melt sort of not really timing, but the initial rate of snow melt to be higher than what it actually was. On the positive side, though, we can clearly see that the machine learning algorithm worked very well, which is very promising, because it's quite easy to set up, and meaning that we could easily transfer that model very quickly into another area. And then on the right-hand side, so the eastern part of the basin, we see again that the simulation of Earth observation-based snow water equivalent data actually improved the forecast results quite significantly. Unfortunately, because I'm not sure if you guys can see the graphs or anything, so it's kind of hard for me to go through them in much detail. So let's just forego that. I'll send the slides later. Okay, so as I said, we're also providing seasonal forecasts, so ensemble forecasts. So what we do is we divide that seasonal forecast, 90-day seasonal forecast, into 3 periods. So we have from 0 to 30, 30 to 60, 60 to 90 days lead time. Reason is that if we try to put all the forecasts sort of into one prediction, it becomes a garbled mess, and and the forecast tends to get like really highly attenuated and skewed sort of towards the latter parts of the sort of forecast lead time. So this is quite difficult to actually explain, but this shows the situation where we had this spring. So we were predicting, so what we're trying to predict is like, what's the probability of peak flow occurrence, because that's really the most crucial thing for the hydropower company, and what that peak flow rate would be. So we were predicting with the seasonal forecast that we should see a peak around mid-May with a 16 and a 22% probability, and then from there onwards the probabilities sort of tend to decline. And we were predicting a peak flow around 950 to 960 cubic square meters per second, and the actuality was the actual peak flow time was May 15th and 750 cubic meters per second. So we got the timing kind of right, you could say, but we overestimated the peak a little bit. But overall, the seasonal forecasts tend to unfortunately be sort of skewed again, even though we're cutting this into these 3 periods, sort of to the latter part of the forecast. So we still need to work on this, but overall it was quite okay for the Kemijara. This is the eastern part of the basin point that we're looking at. For the western parts, there was a lot of spread in the seasonal forecast, so it was even more skewed towards the latter parts. So we kind of got that this one wasn't as successful as the Kemijara one. Although, okay, so we predicted so basically what happened is that the peak flow occurred when we were predicting only a 6% probability of it occurring at that time. And also we really overestimated the peak flow discharge at around 1,000 cubic meters per second, where in actual fact it was 775 cubic meters per second. But anyway, so this is kind of all I wanted to discuss. There's still a lot of work to do, and it's not really surprising that the seasonal forecasts are difficult. I mean, it's a well-known fact, and we might have to go back to the drawing board on this one. However, at least with the machine learning algorithm, I'm very positively surprised that it works so well, and that's very promising for future development efforts. Okay, that's all basically from my side, and if you have questions, you can ask now or maybe later during the Q&A sessions, and I'll upload the presentation later.
So thank you, Jaakko. It was very interesting presentation, and it was nice to hear that you are also using Earth observation data in that. So if there's no questions, not in the chat at least.
Yeah, it's a shame that you guys couldn't see the presentation properly.
Well, almost everything.
Okay.
So then it's time for the next presentation, and the topic of the presentation is global carbon and greenhouse gas emissions, and it's presented by Ville Kasurinen from ICOS. So is Ville here? So you are muted, Ville.
Oh,
Thank
can
you.
you see the slides now?
Yes.
Good. Yes, so I will give a presentation regarding the progress of global carbon and GHG emissions from this pilot very shortly. How can I change the slide? I can share it, but this one then. Yeah. So we have pilot partners, ICOS head office. So I'm the coordinator of the pilot. And then we have Max Planck Institute that has developed this kind of FLUXCOM product, which is data-driven global model predicting net ecosystem exchange and evapotranspiration. It's using eddy covariance flux measurements from several towers globally, and then ERA5 climatology, and then remote sensing based vegetation maps and so forth. And then we have a FMI, and their task is to do comparison between FLUXCOM product and then CO₂ satellite and CAMS products. And then we have ocean domain partners from University of Bergen and Exeter. And we have finally made some comparisons between the FLUXCOM product and FMI machine learning prediction method, and also inversion model called Carbon Tracker. And maybe the most important or significant result in this comparison is that while the different methods predicting the net ecosystem exchange is working quite well for many different Transcom regions. So there are problems with the Northern Africa and Southern Africa and Australia, at least in this comparison. And the most probable reason for this, in a way, these large differences is that there is some kind of error in the FLUXCOM simulations. And they are trying to figure out that what is causing this big gap between these different methods. And here is the same thing, but as XY scatter plot. And for the same regions that we observe these problems, like Northern Africa, Southern Africa, and Australia, the fit is a little bit not that good than compared for the Asian temperate or European regions. Then Hanna-Kaisa Lindqvist made also this kind of comparison between CAMS Global CO₂ atmospheric inversion product. And there is some detailed information regarding the prior fluxes that CAMS is taking in. And here are some visualizations how the satellite data looks like. And these comparisons has been made like in monthly data, because the density of satellite data is not similar than FLUXCOM, which can be in a way, or the highest resolution FLUXCOM from FLUXCOM is like 1 hourly fluxes, so that really doesn't work with satellites. And the results between FLUXCOM and CAMS comparison are fairly similar. It works for most of the regions, but then there are some differences, for example, in South American tropical and Northern Africa and Southern Africa and Australia. So this in a way confirms that this FLUXCOM product might have some unsolved issues still before it can be used to this kind of global comparisons. And then there is a calculated difference between this FLUXCOM net ecosystem exchange and CAMS biospheric flux. And it shows similar results than already explained, that it works a little bit better for some regions and then not that well for others. Yeah, but interestingly, in a way, the surface and satellite differences between these CAMS and FLUXCOM are a little bit smaller and comparing the CAMS product than that when comparing this carbon tracker or FMI machine learning like algorithm. Then the ocean domain is developing at the moment notebook that is collecting the input data for calculating this ocean atmospheric CO2 fluxes, and they are building the notebook in such way that these basic calculations can be executed in the notebook. And if the remaining project time and available manpower in University of Exeter and Bergen allows, they will try to develop more advanced interpolation and gap filling techniques. And the aim is to publish a notebook in IGOS Carbon Portal Jupyter Hub demonstrating the progress that we have done during the eShape project. And then there are some examples regarding the ocean domain fluxes, which is based on IGOS and SOCAT gridded data, and then calculated flux, the mean flux between 2000 and 2009, and 2010 and 2019. And here is more or less the same thing, but shown as a time series. And also the right-hand side lower plot is CO2 flux from the English channel. Yeah, that was all. Thank you.
Thank you very much, Ville. So it was a very interesting presentation, and it was interesting to see that it depends on the area. That's how good the results are. But is there any questions if somebody wants to ask now or maybe later in the questions and answers session? So if there's no questions now, we can proceed to the next presentation. So the next presentation is Weather and Climate Service for UNESCO Cultural Heritage Monuments, and it's presented by Stavros Solomos from the Academy of Athens or National Observatory of Athens also. So
Yes. Okay.
thank you.
Hello from Athens, Greece. So yes, this is the pilot for the seasonal preparedness regarding the climate heritage monuments in Greece for the time, and this is something that is already included in the success stories of eShape project, and the idea has to do with the very many historical sites in Greece that have been defined by UNESCO's cultural heritage monuments. And since tourism is strongly connected to these heritage destinations, we have decided to design a specific web portal for short-term and mid-term weather information and climatic information for certain areas such as the Acropolis, Delos, Corfu, Meteora, Delphi, and so on. The information is based on Copernicus data from the C3S SMWF service and the ERA5 dataset for the climatological analysis, and also from a high-resolution WRF model that is running over Greece at the 4x4 kilometers grid space. Of course, this service can now be expanded to include not only more destinations in Greece, but also more destinations in other European countries and worldwide, if this is needed. And actually, there are such plans because the preservation of cultural heritage in the frame of climate change is a big subject, and we are also working in this direction. This pilot has been co-designed with the Institute of Greek Tourism in Greece, in Sete, and within several meetings with the scientists there and the people that of the Greek Tourism Institute, we came up with certain practical issues, such as that the tourists in Greece have several options on which places to visit during their time schedule. And the suggestion by INSETE was at this place to focus on cultural heritage monuments, so as to have a start with something that is very emblematic, and of course to go with a simple user-friendly interface that could be actually used on a day-by-day basis by the end users. As you can see on the map, there are certain destinations like monasteries, Patmos, Delos, Acropolis, Olympia, Meteora, Delphi, and so on. One question that we very often have is that Crete is not yet included because there is no officially a UNESCO monument on the island, although of course there are very important monuments on the island, but this will be soon an addition there. And the methodology for this development is now published in FMI research letters, and in short, we get the R5, the CIFS, and the WRF models for the different time scales. And so we derive the local climatology, the local seasonal forecast, and the short-term forecasts. And this is afterwards presented separately for each destination. Now this is how the service looks if you visit the link below. So the user has the choice to select between a short-term 4-day forecast or a more climatologically based seasonal forecast. That is, of course, produced from the ensemble members of the CFS. So this is a statistical product and is compared to the local climatology. But also you can get basic information on the selected destinations, not only regarding the anticipated weather conditions with temperature, humidity, wind, and so on, but also a few words on the importance, on the history behind these monuments. So one could, let's say, make a choice based on several criteria and plan their visits. The 4-day forecast is presented in simple format with for its destination for the next 4 days, and so is the seasonal forecast for the next couple of months. And of course, for the more interested user, you can go and look into more detail in more sophisticated graphs on a time series of temperature, of climatological and seasonal forecasts of precipitation, both for rainfall and for snow, wind graphs, humidity time series, and so on. So you can get a more detailed information on the area. And on the practical side of this development, from the end user, let's say, side, this is a real life example for some people that own an Airbnb apartment in an area near Poros, an island in Peloponnese. So the idea is that if someone is visiting their place, which is here, you may have several options for a day trip to many interesting areas like Delphi, Athens, Corinth, Olympia, and others. And in the planning of such short-term excursions, weather and climate may be an additional input so as for someone to select and plan their holidays. And so yes, this is the feedback from the owners there of that place. I don't know if you can also listen. Maybe you cannot listen, but they, in short, they say that how they use the pilot to assist their visitors on deciding how to visit areas that are near their place. And this is the situation more or less for other let's say owners of small Airbnb apartments, or for hotels, or for tourist operators who want to provide their visitors with advanced information on during their holidays. So this is from our part. I don't know if you have something to comment on this. And thank you very much all for being here today. Hello, Mikko.
Hello. So I do have a question and sorry for coming late now, but there was another project that needed a kickoff. They couldn't organize it anywhere else. So thanks, Katrina, for taking over for hosting this. But Stavros, I was interested if you have any kind of feedback channels for end users for this service, and if that is kind of what is the message in them generally.
Mikko, you've been yourself in Athens. Did you use it at all or not?
Yeah, I must say that I did not have any choices anyway.
Yes,
the program was full enough that the only destination could be the Pantheon. And I did visit that only from going around it at 11 o'clock in the evening or like nighttime, which was beautiful. But in essence, I would have done this probably in all possible weather situations. But
we have some feedback. We have some channels for feedback, but mostly this comes from through the tourism federation, the INSET, and we had also a presentation for them a few weeks ago. I can say that there is not so many people using this service right now, but it looks like they are disseminating this through their channels. And another important thing is that here at the Academy of Athens, we have started to concern very much on subjects that connect cultural heritage with climate change. So this start that we made in the frame of eShape is now, we're trying to put this as a starting point also in other proposals and projects, with the hope that this can be expanded to something more, something bigger. And to be honest, our let's say ambitious targets would be to work also together with some archaeologists and people that work on the preservation of the monuments, so as to come closer to what actually this means for the monuments themselves. But yes, the service is up and running, and we're here to support it.
And that's, I think, super good and important, I think. But I do, well, it's probably for all the pilots in eShape, like one key question and difficult task is not the service itself, but it's actually how to get marketing, how to get more people aware of it. So nobody gets on the internet by chance to any website. Yes. So someone needs to, and I think this is very nice with your service, that you do have a clear kind of promotion agency by having this insight in here. But in essence, it's the question, how effective are they? For example, if Airbnb, as you were using it, would kind of link to your service or kind of bring in something from your service to their information, that might be much more than getting flow to this service. And I think that's one of those questions that I wanted to raise here, just like what we need in eShape to maybe write down is, okay, we made services, we had some end users, and it looked to be what they needed. So I think that is important. But then there's the next step of to expand it quite radically much more. That step, like what can we kind of like do for it, is maybe not so clear. And I think we should write this down somewhere, or any idea we have on it is something very useful for eShape end reports and motivating the next steps. But hey, thank you very much, Slav.
Yes, I agree. Thank you very much.
So, Katrina, go on.
Thank you, Tarek. And Tarek, yeah, I was just wanted to say that there's also the eShape help desk platform that aims to link users and the pilot teams. So you can also go there to visit the platform and send questions there and comments and suggestions. So the last presentation will be future climate projection of heat indices for Austrian major cities, and it is presented by Maja Juvela-Aloise from the National Meteorological and Geophysical Service of Austria. So you are welcome to present your presentation.
Thank you. So I will try to see my screen. Can you see my screen?
Yes.
Yes. Okay. So I'm here to present our pilot for the future climate projections of heat indices for the cities in Austria, about the downscaling of information on an urban scale, for the part of the team. This pilot is part of the climate showcase, together with the German Weather Service pilots on seasonal forecast for German cities, and the FMI pilot for seasonal forecast for Helsinki. Our pilot is on another scale, so going on a climate projection, decadal or even centennial scales. And we are focused not on snow or precipitation, but just on the heat and the urban heat island effect in combination with the climate change. So what we are doing, we are trying to downscale the climate scenarios which are available on global and regional scale from the different GCM and RCM outputs on the urban scale, which will include the urban structure and therefore the information of the heat load produced in the city together with the regional changes. So what we produce are high resolution spatial maps of typically of 100 meters with the dynamical statistical method. And this information is then used to evaluate urban hotspots or cool zones and also the future development. It can be then further built on the modeling results for adaptation, for urbanization effects. So it's used normally for the urban development plans, risk management, environmental protection. Our main stakeholders are the city administration. However, the end users can be also other researchers, private companies that offer expertise for the cities, consulting, or media, or even public. But we are at the moment focused to provide information for the cities. The pilot was developed for Vienna with the intention to use as much as possible available Earth observation data also on European scale, so it could be upscaled or standardized for other cities. Because we adapted the methodology from the German Weather Service, so they are also using this model, but each city has its own data, so it's not very easy then to compare. We have used, for example, Urban Atlas, which is a standardized mapping of the city's land use, and other Copernicus land monitoring services, like for the tree cover density, ceiling, and we noticed that in the results, there is also sensitivity to these inputs. So the better results are when we use high resolution data. So for example, we have the land information system of Austria in 1 meter resolution on land cover, which we then enriched these results. So it's possible to do also on the European scale with some assumptions, the simulations, but it's better to use the local data. For the meteorological part, we used a regional model output from Eurocortex project, the different combination of GCM, RCM data, normally for wind, temperature, relative humidity, but daily time series. The period is 2011 to 2100, and we used 2 RCP scenarios. And then as a result, we get the climate indices, so days above a certain threshold. So for maximum temperature, 25 and 30 degrees. We also extended it for 35 degrees, which was because it was starting to be more interesting for Austrian cities. Although the best results we get for the summer days, so the threshold 25 degrees, which is still quite a robust index, and is also one of the standard indices for climate evaluations, and also for the night, for tropical night. So we see in Vienna hot areas inside the city and cooler areas where is the forest and orography, so higher elevated areas. And at night, the pattern changes a bit. It's more homogeneous, and it's also concentrated in the dense built areas. The methodology is, as I said, adapted from the German Weather Service. It uses the dynamical model, MUCLIMO3, so microscale urban climate model, with different static data from the city, from the land cover, orography, terrain, but and meteorological data for the daily cycle of the evolution of atmospheric processes in the city. So it has also soil model, radiation model, and surface model. A lot of processes are still parameterized on 100-meter resolution, for example, shadings and also exchange with roofs, and then the vegetation model. And we have then outputs on a daily basis for minimum, maximum temperature, for example. And this output is then combined in a statistical method called the cube-weight method into climate indices. So it is weighted for each day the temperature it is not then dynamically calculated because it's computationally expensive. So we can, after the simulations of the dynamic part are finished, relatively quickly calculate different climate scenarios using just the time series from different regional climate models. So we get maps for number of summer days, for Vienna, for future or past or future, and for different scenarios. And these data were produced not only for Vienna, but also for other major cities. We couldn't say capital cities because we are missing some, but they are also not very big cities. So it's also the cities where we have our regional offices. So we have more support for the users and good cooperation with cities. And but it's also, we have also examples for other cities that are not on this list. However, we cannot cover every city or and the data have been visualized or put or published on the data server of the climate change data center Austria. So this is a data center that is operated at our institute, but is in fact a collaboration of different institutions in Austria, and different kind of climate data are there published. Also the regional climate model, and it is not big system that also has its own structure for the metadata, citation, version tracking, and visualization of the data. We provide data in raw format, in netcdf, but also you can download different kind of pictures. So I have a small example how the animation looks like for the summer days from 2011 to 2100. So you can see every year annual number of summer days changing from the map, and you can see the time series. This is the point in the middle of Vienna. You can change the point for the time series, and you can track the evolution of the urban heat load. We normally provided this kind of data for the 30-year averages, but we often get questions about how it looks in extreme days. And you can see for this kind of index, the variability is very high. So even if we have an average some 70 days, it can go over 100 or under 50. And then it started the questions how this data will be interpreted, how they will be used, whether this visualization is enough. A lot of cities have, or for example, Vienna or bigger cities have their own GIS systems. So maybe they could just download data and plug the output somewhere else. Or maybe this system could be developed. So or whether they need also support for interpretation. So this raised a lot of questions for us. And that is the reason we started the survey in May, and now it's running up to end of June. First with our regional offices, how they are using this data and whether it helps them to prepare the presentation or communication with the cities, and then also with the cities, what are their data needs? We have these indicators, but we also wanted to know what other parameters they will be interested to have, how much experience they have to work with these data. From the data platforms, if this is really the place where they will find the data, because there are also an initiative for open government data. So the city data are also saved somewhere else. So we have the different options, and also whether they prefer to have this data restricted or publicly available, and also for the analysis and visualization, whether these kind of tools are good enough or could be developed. And when we have the results from this survey, we then intend to publish the results for other cities and continue the communication for future developments or applications. Okay.
Sorry, but
yeah.
I don't see the slides at the moment. Should they be visible?
Oh, it escaped. Oh, sorry. This
probably two slides at least were not kind of like.
Yeah. Okay. This was this one. So this one you saw.
Yes.
No, it was one before that one. I think is the last one we saw. We'll go. Oh no. Okay, there were more slides that we did not see. I think that's the one that I at least can remember. Then maybe the next three. But I think your explanations were still also good enough to get a good understanding. So thank you very much for this.
Yeah.
I have this kind of like commentary question-like thing that when your service is the one where there's not a specific dedicated web page for it, it makes it so much more difficult to have direct insight in a way. Because I think what you could get in your example, I think, is good to understand that if different cities have the same information, but some cities are using it, some cities are not using it, then what is it else that they have in these other cities? That might be something that you could see. So I don't know if there's a way of getting this kind of information from those where you are distributing data files, for example. But in essence, I think this is a question of yeah. I think it is very useful to have a web page or a web system to also give insight. Even if you produce data can also be used, of course. But the point is that with your own, and now hopefully I don't go out of battery. This is what my machine is saying. Yeah. So I don't know if there's. Did you have any plans to actually make a web page also just to kind of disseminate this information? It also sometimes kind of broadens the kind of use of it in general.
I think if we make a separate web page just for that, we will have even more difficulties to get the users use it, because then it's just for this specific purpose, and the data center is where they could find also other data. So it's more likely that they, even if they were not looking for it, other users could also find it better. Because the data itself, because we have already cooperation, so the data they could also get from us directly. The question is whether they will use the server for that, and this visualization and everything else. And then is also the question of technical support for the maintenance of the page, because also these platforms change, and we wanted to have some robust solution where it's not dependent on a project, that it continues and that we are sure that somebody will.
Yep.
Yeah.
No, but my question or my comment, it's more a comment. Consider Vienna alone. In Vienna, you could, by having for example, a service where you can zoom into the data, you could see where in Vienna are the areas that people are interested to look at this information. That alone is already something which is on itself would be interesting information to pass on to Vienna, that these seem to be places where people are or businesses are considering that, hey, how is this going to develop, that we are already heat stressed, or hey, the stress has come on. So I think this level of intelligence is what nowadays the kind of the data intensive kind of industry, because I think there's a very big shift nowadays that it's not just like the data industry itself is important, and you only get that information if you are on the internet yourself covering it. Like, you will not get this level of information from your kind of other platforms where the whole data sets are, for example, given out, because I think the subset, when you have many information sets, they are big, they have details in them. If you give it in one go, all of it for a city, for example, this inside of the city information is lost. And that's why I'm just promoting it. I totally understand that your solutions was like this, but just to consider that if you want to kind of like carry on with this or similar things, there is a very big kind of like motivation that you should consider, which is this kind of being able to know how. And nowadays, just an example, when you are using whatever web pages, how you use it is combined with all the other people using it. And that information many times is something that can be sold onwards on the internet for profit. So you understand that the economic value in data is nowadays not just the data, it's also the use of the data. And you only get this information of the use of the data if you control the source where it goes from. And I'm not saying that you have some control if you go to a kind of like academic kind of data repository, for example, but it's definitely much less granularity, and you have no control of what is being looked for in the same way if you run your own websites. Especially Google Analytics has made it also pretty simple for anyone. If you just accept that Google Analytics is running on your site, that you can go after these single users of these things, you know, from where they come. You can make even kind of like profiles of them. So this is for us to understand as a community doing these services that the world has changed in this sense, and it means that we have to do a little bit more, which is not like our core function necessarily, but then we are in a new kind of like opportunity for doing value in society. But in essence, I think this is good. I don't have as such much more to say.
Okay, thank you. So yeah, so what you're suggesting is to have this expert insight already integrated data, so that somebody doesn't get the default with information.
Okay, maybe it's difficult to understand, but when someone goes to a web page, all kinds of things are being monitored, logged, and make statistics.
Okay, the statistic is tracked on this web page, but it's not. Yeah, thank you. Can not input.
Thank you, Maya. So did the presentation already end? So there's no more slides?
Yes, that was all. Thank you.
Okay. So I think maybe Mikko's computer went out of power or something. Oh, well, maybe he will join us again after a while. But thank you, Maya. It was very interesting presentation, and it was nice to see the visualization of the climate indices. So I think there was all the presentations, and then we should have the discussion and questions and answers and closing. But Mikko Stralendorf should be keeping the closing, so we can try to wait for a while if he will join us again. But at least there was already some discussion with Mikko already. So does anybody have any questions to the presenters at the moment? So is, for example, Jaakko there or still?
I'm still here, yes.
Yes, so I just wondered that if I could ask some questions from you. So you have some key users for your service, I suppose. So
Yeah.
is Kemijoki the only one, or?
Yeah, at the moment that's the only one because, well, that area, I mean, there's not many stakeholders there, so that's why. The idea was to expand this service to cover the entire country, or at least part of the service to cover the entire country. So we would have had, for example, the Finnish Defense Forces as another key user, but they have switched priorities, understandably, and also are not interested in publicly sharing this sort of data on land surface conditions. So at the moment, no. But another thing is we're expanding this service to Milan and Sofia, so Italy and Bulgaria. So then we'll have more users. So, but we just need to configure the models and everything for that area. It's gonna take a while, but something similar to what we're doing now is what we're gonna do for them there.
Okay.
Yeah.
That's nice to hear that you are expanding elsewhere also. So I can't see Mikko Stralendorf here, so maybe.
I think his battery died, so he probably won't be able to charge it because if his battery was dying and he didn't have a charger a few minutes ago, I doubt that he has one now.
Yeah. That's maybe the case.
Yeah.
So is there somebody else that would like to give some questions or? Or maybe we just have to close this already.
Yeah, let's close it. There's no questions. I don't think Mikko's coming back.
Yeah. That might be true.
Mm.
But yeah, thank you very much for all the presentations. It was very, very interesting to hear about all of them. And this has been recorded, and I think the recording will be available in eShape's YouTube channel after a while, and people who didn't have a chance to join this can watch it from there, and also you can watch it if you didn't you want to look something again from the presentations. So if there's no other questions or comments, I think we could stop this, and I think you get some questions more from that eShapes help desk or somewhere else. So thank you very much.
Thank you so
for
much,
all of you.
Katrina, and everyone
Yeah.
being here.
Yeah.
See.
Thank you.
Thank you.
Thank you.
All right. Bye.
Bye-bye.
Bye.
Bye.
Bye-bye.